Hey folks, welcome back to another video in this series on quantum computing made easy. So finally we are ready to code up the quantum solution to the Bernstein-Vazirani problem. If you haven't checked out the previous two videos where I discussed the classical solution and the theory of the quantum solution, please do so because I will be using all of that information. So yeah, so let me quickly just jump in the solution. First of all, let's remind ourselves what our circuit looked like. First things first, we always, the solution was a single query process, and we started with a 0 qubit state, and the number of bits depended on the number of bits in the problem, and then an auxiliary state with a minus sign. We applied Hadamard to each of the 0 bits, and then we applied the oracle coupled with this auxiliary state to perform the computation that we wanted. And then we applied the Hadamard again to get the inverse, and that gave us the secret string. So this is how our circuit looks like. Two sets of Hadamards and then oracle in between and the auxiliary state. So let's look at an example first, and then I will code it up, or rather just walk through a code. So this example, I have directly taken it from the Qiskit documentation. Let's say we are dealing with an n equals 2 state, or rather 2 qubit state, and my secret string is 1, 1. So first I start with a 0, 0 state. Like I said, you always start with a 0, 0 state, and then you apply Hadamard to both the bits. So applying Hadamard to both the bits gives you this state. So when you apply Hadamard to the first 0, you get 0 plus 1 divided by square root 2. Then you multiply it to the same thing again, and this is what you get. Now, if you remember from the previous video, the way a quantum oracle works is it takes in the state, and then it gives you -1 to the x dot s and the state back, where dot s is your secret string, which here is 1, 1, and that's why it's 1, 1. So when we apply this operation to each of these four states, this is what we get. And then applying a Hadamard again. So you would have to like do it on a pen and paper, apply Hadamard again, and then you would see that the only remaining state is 1, 1. So starting from state 0, 0, applying a Hadamard, and then this quantum oracle gave us back the S state. So this, we obtained our secret string in a single shot fashion. So basically this is what we are going to do. So let me jump into the code. All right, so here we have the same notebook where I first demonstrated the classical solution. And now let me show you the quantum solution. Again, this I have just taken pretty much like modified a small amount the code from the Qiskit documentation, and I will just walk you through what we are doing. First of all, let's import Qiskit and the simulator quantum circuit, and then assemble, and then some visualization utilities as well. So let me just run that. Now we get to the quantum solution. Let's say it's a 3 qubit problem, and then my qubits are 0, 1, 1. So first of all, I create a quantum circuit of 4 qubits and 3 classical bits. Why 4? Because it has to be 3 plus 1, because there was one auxiliary bit as well. So that is why 4. And then we need, so for each qubit, you need a classical bit to store its measurement. That's why 3. We don't care about the auxiliary bit, but you can keep that around. But then again, we don't care about it. So first of all, we need to put the auxiliary state into, so n here is 3, 0, 1, 2, 3. We put the auxiliary state into the negative state. That is done by applying a Hadamard gate and then a Z transformation. So either you can do that, or I can, so in the previous videos, how I was setting the initial state, you can use that as well. So multiple ways of doing the same thing. So this sets my initial state into this particular negative state. Good. Now I apply Hadamard to the first three qubits. So I apply Hadamard, Hadamard, Hadamard because all the zero states get applied Hadamard. And then I need to apply basically my quantum oracle. And now this is the tricky bit. So quantum oracle we apply according to, so let's get back to um, how the action of oracle worked. So give me one sec while I pull it up. Right. So if I bring this up and let's look at this second law. So the oracle, what it does is when it acts on a state, it gives you -1 to the action of that state on X. Now this is equivalent to 2, like I demonstrated in the previous video, where oracle acting on the state and an auxiliary state gives rise to X, and then this is an outer product, and then Y C naught f of X. So this is what we are trying to model. Now, if f of x is 1, then y gets flipped. So it's a C naught operation. And if f of x is 0, then there is no flip. That means it's identity. So that is what we will map. So since we already have access to, what the secret bit is or secret string is, I can just go and put in whenever the secret string is 0, put in an identity gate, and whenever the secret string is non-zero, put in a 1. Oh, I'm sorry. So whenever the secret string is 0, put an identity. Whenever the secret string is 1, put a C naught. That's it. And then after that, apply Hadamard to the remaining ones and then perform measurement. So let's draw the circuit. Okay, it looks a bit messy because by default, Qiskit orders when you plot a circuit in Qiskit or use the dot draw command, it orders things by its depth. So the order of operations, so first the Hadamards are there, and then the I and Z operations, and so it orders things by depth or level in a circuit. So that's why this looks messy. So to get rid of that, we can prevent that from happening by making barriers. Um, so by constructing, I think, is that the command barrier? Oh, well, I guess that's it. Okay, yeah, so it created a barrier here. So let me create 3 barriers just to, make it easier. I'm not sure if barriers have some real world implications as well when it comes to um, generating the code and transpiling it, but okay, this is a bit more readable. Let's see, have I made a mistake? No, I haven't. All right, let me again tell you what's happening. So first of all, these 3 are my main qubits, which I always start with 0. Q3 is also starts with 0 to begin with, but then after an H and a Z gate application, it becomes a minus state. So at this point, I have 0, 0, 0, and a minus state. All right, step 1, apply a Hadamard to the first 3 gates. All right, that's good. And then the last step is apply a Hadamard again to the last 3 gates and then measure them. Good. So this and this part is easy. Now, in the middle part, what we are doing is basically whenever the bit is 0, put an identity. So the first bit was 0 because if I look here, S was 0, 1, 1. The first bit was 0, put an identity. And the second and third bits were 1. That's why we are doing a C naught operation. C naught where the control is this one. So that's why we are doing the C naught operation. And let me explain the C naught again because it's a bit tricky. I also get confused. Right, so this is the action. X is your string X. Y is your auxiliary, which here is a minus. And when I apply my oracle, it gives me X. And then this is the same as cross outer product. And then I get a C naught of y, the auxiliary one, C naught f of x. Now, if f of x is 1, this becomes, we have to invert it. So it's C naughted. And if it's not, you get y back. So that's why. So wherever we have 1, I am performing a C0 operation. All right. So that's basically the circuit. I perform C0 on uh, qubits 2 and 3 and let the first one be as is because that's 0. And then I just run it on my circuit and then I get 110. Uh, so we get 110 because it's an inverted. It should be read as, you should read it as the inverse of that. Now suppose if I had 111 and I run it, you see I get 111. So let's try again. So um, actually, let me comment out this inverse thing. That's the one making the issue. What if I had 101? I get 101 back, and here you can see the middle qubit is the one that is um, identity, and the first and last are the ones that we're noting because those were one. So this middle block is the quantum oracle. That's an implementational thing. So that's not the thing to keep in mind. Just think of it as being the oracle, a black box. The two Hadamarts are the ones that are doing the task. So in one go, we pass in a string of zeros and we get S out. So what we measured is your string 101. So that's basically how a quantum algorithm speeds up over the classical algorithm. And you can see it's not the same. Like quantum algorithms can only be applied to specific problems. So like problems like this where you can get a speed up, they can't just be willy-nilly applied to, speeding up a for loop or something like that. It only applies to a specific class of problems. I will upload this video on my GitHub page, and well, most of the quantum code is based on the Qiskit example, so you can check out that. Um, the Qiskit documentation and also the Microsoft Quantum documentation is awesome. Qiskit textbook is awesome. It has way more algorithms to play with around, and also some recent algorithms, image processing using quantum algorithms, some fancy stuff, machine learning. So definitely give it a try because uh, it's the possibilities are endless and there's a lot of things to explore and try there. But as far as this video series is concerned, I think I have explained all the important bits. We went through an algorithm, and anything else that you encounter would just be a combination or a more complicated version of things that we have already encountered. So I feel like I have covered all the basics that you will need in your quest to, delve deeper into quantum computation. So I think this is a good ending point for this series. Let me know how you feel in the comments and please like and subscribe. And I will see you guys again in a new series. I don't know, maybe on JAX or some deep learning theory, but haven't decided yet. But thanks for sticking around till the end of this series, and I will see you guys again. Bye.